want to get into the sensation and perception unit. If you are in class with me, we're actually already starting on some of the basics of sensation. And so I'm going to get in to the eye part of our unit with you right here now through virtual. So let's just start talking about the eye in general. We're going to start talking about the cornea first. The cornea is the transparent bulge on the front of the eye. It's the kind of part where light enters into, and think of it as like that protective layer. Last year it was perfect because I always related it to Mrs. Cornea, and I kind of said how think of Mrs. Cornea as like protecting that baby bulge. So we can still think of it that way. If you've ever seen pictures of Leo and Hannah, they're absolutely adorable. So the cornea is that protective layer at the front of the eye. The pupil is a small adjustable opening on the eye, like the really small part. If you've ever seen pupils dilated or constrict, think about that. That's part of our sympathetic nervous system that actually happens automatically. It allows the light to enter. And so it's the iris that actually opens it or closes it, constricts it to allow the amount of light to enter. If you've ever been to the eye doctor and have your pupils constricted, you understand, like they're really trying to get a good look at your whole eyeball, if you will. The iris is that colored part of the eye. Think of an iris as like a flower, a colorful flower, and that's the colored muscle that surrounds the pupil, that dilates and constricts the pupil. I love looking at the color of people's eyes. I know it's kind of weird and creepy, like I want to look at your eyes, but I think they're truly like the soul of people's eyes, and so I think eyes are really a cool thing to inspect on others. The lens is a transparent structure behind the pupil that changes its shape to help focus the image on the retina. If you're at all into like photography, you understand like how you have to change the lens to get like a good clear view. This is what the lens is doing for your eye. It's helping you focus, helping you get a clear look at the images on the retina. And the retina is coming up here. We're going to talk about the retina on its own slide because it's really that important. So these are just kind of the front parts of the eye, and you'll see my my little model right there of the eye. What I would like you to do is try that handout. Just try it on your own. See how you do. You know, you don't have to turn it in or anything, but see if you can label the parts of the eye. And maybe there's a page 104 in your book. See if that would help you as well. Oh, I have to talk about accommodation. Okay, so maybe you notice I'm wearing glasses. Like I never wear glasses. Well, now I do. Because what has happened is accommodation is how our lens has to shape. The curvature of our eye has to change to accommodate near or far objects. So when this is when Garrison was a baby. So like 16 years ago, I had LASIK eye surgery, and I had it done, and I asked the surgeon, like, how long is this going to be good for? And he's like, well, you should probably get about 20 years out of this, that you won't need to wear contacts or glasses. I'm like, sweet. Well, my eyes have changed very rapidly in about the last 6 months or a year, and I realized I need glasses. So I suffer from what's called myopia or nearsightedness, where I have problems focusing on things far away. Like, you do not want me driving at night without glasses. That's what I realized, is I got a problem. Because the light focuses the object in front of the retina. Like the question that they're going to ask on the AP test is not about nearsightedness. They're going to want to know, where is the object focused? Is it in front of the retina or behind the retina? In nearsightedness, it's in front of the retina. If you have farsightedness, which is called hyperopia, this is when the lens focuses the object behind the retina. And again, we're going to talk about the retina a lot here. This is what we see actually in older people when people have trouble reading things that are up close. So if you are seeing your parents like reading like the missalette or like the newspaper like this, it's because they're having trouble focusing. Now here's the kicker. So I go and I get these glasses, and I'm nearsighted. Like I need to see things far away. And the doctor's like, well, do you want to get bifocals put into your, like bifocals are part of like the lens. Do you want to put that into your glasses? I'm like, no, I'm not. I don't have farsightedness. Like I have trouble seeing far away. And he's like, yeah, but you will. I'm like, oh, come on. I'm just going to be blind. Anyway, so this is how our lens changes to focus objects far away or close up. Now let's talk about the retina. The retina, think of the retina as like the workhorse of the eye. All the other parts of the eye are they're great, they're important, but it's the retina that does all of the real work. And that's at the back of the eyeball. If you saw that screen before, it's at the back of the eyeball, and it's what converts that information into neural signals. This is what sends the information onto the brain. So all the real hard work of transduction, if you're coming to class with me, you're going to hear about transduction. If you've already had me, we talked about transduction into those neural signals. This is where the conversion of light energy happens. This is where all that light energy takes place. And it happens in the form of either rods or cones. So rods are these little receptors that are in our retina that processes black, white, gray, like all the basic color. And then cones are for color. Think cone color. That's an easy one to remember, right? Now look at that little inset there. If you look and see, like the rods are the ones that are like the gray receptors, and then the cones are the ones that they highlighted for us in the purple receptors. You can notice that there are so many more rods than cones, 120 million compared to 7 million. And you might have to ask yourself, like, well, why? Why are there so many more rods than cones? Think about it evolutionary wise. It is not imperative for us to see color. It is imperative for us to see like shadows and in twilight and see as much as we can in the dark, because we don't want to have somebody like come over the back of us and hit us over the head when we come around the corner from like our hut or something. So if you think about it evolutionary wise, it's much more important for human beings to have a lot more rods than cones. Okay, so rods and cones. Where we find these rods and cones densely packed are, I should say cones, not rods. Cones, densely packed, are in what's called the fovea. And the fovea is just this like little tiny part of our retina in the back of our eye. And this is where we get our sharpest vision and fine detail. Think of this as like the high definition part of your eye. Like you got standard definition and you got high def. Think of the fovea as the high definition. Also near the back of our eye, near the retina, we have this place called the blind spot. Now, if you're driving, you understand what a blind spot is, and it's kind of the same is true with your eye. It's a point at which the optic nerve, which we'll talk about here in a second, the optic nerve leaves the eye, and it creates this kind of blind spot because there are no receptor cell there. Now, what I do have to say is that like what one eye can't pick up, the other eye tends to do. Like what one eye can't catch, the other one can. But sometimes like you can't. So here's what I say. Cover your eye and then like focus on the plus right there, cover one eye and come in closer, or bring your iPad like closer to you, or you go in closer to your iPad and see the point at which you cannot any longer see the elephant. That's your blind spot. All right, so we all have kind of this area is near what we understand is the optic disc. Also, when you come to class on Thursday or Friday, we'll do this little like demonstration, and we can see where your blind spot is and kind of how well your peripheral vision is. Okay, so how do we process visual information? So there's kind of this whole series of events, like with the action potential where it starts here and then it goes on in this whole series of events. The same thing happens with vision and light entering into our eye that triggers this chemical reaction. So it's the retina which is going to kind of jumpstart this chemical reaction. So once it hits the retina, once you see it, you can see the eyeball there, it's going to hit the retina. The retina is going to start this process of neural transduction, sending that information onto the brain. So the first initial reaction, the first chemical reaction that's going to happen is it's going to trigger these bipolar cells. Now, this is just another type of neuron. We've talked about many different types of neuron. These are neurons in the retina. I mean, that's really all you need to know. Then the bipolar cells activate ganglion cells. Once again, another type of neural retinal neuron that happens. The axons of the ganglion cells, and can you see that? They kind of almost twine together to form what's called an optic nerve. It's almost like a rope-like structure that is formed from the ganglion cells when they form the optic nerve. So from each of our eyeballs, we've got this nerve coming back. That nerve is actually going to go straight to the thalamus. And remember, the thalamus's job is to route the proper information. So when we're looking at this, that optic nerve is going to send the information to the visual cortex via the thalamus. And the thalamus is going to be like, oh, I need you to go to the occipital lobe because you need to recognize that you saw this. Not only so much recognize, but see it. Like, you need to see it. You need to process what you saw. Okay. Oh, one thing. I want to go back. This is really cool. This is really important. That optic nerve can process about 1 million messages at once. At one time, the optic nerve, our vision goes that fast. About 1 million messages at once. The auditory nerve, which we'll talk about here in the next couple of segments, the auditory nerve can process about 30,000 processes at once, messages at once. 30,000 compared to 1 million. Our eyes have a really, really important function for us. But think about how much more important it is for you to be able to see and respond to something than it might be for you to hear and respond to something. Oh, sorry, wrong way. So, stimulus input. This is basic like light energy, which I think you know from probably even like physical science. We talk about things like wavelength, that distance between the crest of one light wave, and the peak of the next. So if if you've ever been skiing, surfing, you understand like troughs and peaks, right? So the wavelength is just the difference from one peak to the next. Hue is our dimension of color, and the hue of something is going to actually be determined by the wavelength. And so when we talk about, you'll see on the next slide, if something's like a bright color or if it's a dull color, if it's more toward a blue color or more toward a red color, that's all determined by wavelength. The intensity is the amount of light in a light wave as perceived by the brightness. That's determined by the amplitude. So these are just a bunch of vocabulary terms that include how we see, the way we see, in this case, color vision. I think that's all we need to really know about that slide. Hue, intensity, amplitude, perceived brightness. So look at this. Perfect. Physical properties of waves. So if we have a short wavelength, that means it's high frequency. If we have a long wavelength, that means it's low frequency. Look at how the distance between those two peaks in the wavelength, look at the difference between those two. If I move this up a little bit, this way a little bit, think about that amplitude, and the amplitude is from here to here. In the small amplitude, great amplitude, bright colors, small amplitude, dull colors. So let's think this is a good one. If you've ever been in Mrs. Henderson's room, Mrs. Henderson on her back wall, she's got like a really like turquoisey, awesome paint color on her wall. Just on that back wall, she would probably have a high frequency, probably great amplitude. So those waves would be like really pretty tight together and pretty good amplitude, actually. If it's something like in my room, I mean, look at these colors of my walls. It's really like drab. That would be more long wavelengths, definitely dull colors, very small amplitude. It's got maybe a touch of like reds in it because it's not quite gray, it's not quite tan or mauve, but it's got a little bit but it's pretty boring. Like, it's not real great color. But our brains have to perceive this. Now, we could get into the whole philosophy of what makes blue and who said blue is blue, but we are just going to look at the measures of these frequencies. So that's actually where I want to stop today. When we come to class together the next time, we're going to look at what's called the Young-Helmholtz, and then we're going to do a little activity on it. But for now, this is all you need to get to the point where we'll come back together in class. So till next time, we'll see you then.